Okay, so thanks everyone for tuning in. Today we have Marija Tomasevic from Barcelona, who I believe is joining from KIDP at the moment, who's going to tell us about her work with Rafael Busso and collaborators on Unitarity islands. So Marija, thank you very much for getting up early, and the floor is yours. Take it away.
Thank you, and good morning. Yeah, as you said, this talk is going to be based on this paper, which I did with Rafael. So here in this talk, I'm going to first review some of the recent developments necessary for the black hole information paradox. And then I'm going to discuss the analysis that Rafael and I did and the implications of our paper for these developments. However, before I start, I would like to introduce some necessary tools that we will be using throughout the talk. Also, if you can't hear me or if you have any questions, just interrupt me. But okay. So the necessary tools that I'll be introducing are the ones regarding the calculation of the entropy from the bulk point of view. With respect, well, we're gonna calculate the entropy for the boundary region using some surfaces in the bulk. So first such tool was developed by Ryu-Takayanagi and subsequently by Takayanagi, and these are called the HRT or RT surfaces. And the statement is basically that the entropy of a boundary region is given by the area of a minimal or extremal surface, so that I'll call X, that is homologous to some region R on the boundary. Here, X and R enclose some spatial region that I call out. This is the meaning of the word homologous. And here is the relevant picture. So we see that the von Neumann entropy of some density matrix here given at this region R on the boundary is given by the extremal area of the surface X of R, and then we want to minimize it all over all Cauchy slices. So this was done in 2006-7. Now, this formula is a purely classical formula. The bulk is purely classical, and so you might wonder would there be any changes if we add quantum effects to the story? And that was subsequently done by Faulkner, Lukowitz, and Maldacena, where they added basically the first order corrections to the surface, taking the same surface and then just adding to it the bulk entanglement entropy, which I have here denoted with this color coding. These red lines here are representing the von Neumann entropy of all the bulk fields in that region. So this is just the first order correction to this previous proposal. And we can see that the area is still getting extremized over and then minimized, and then we're just adding the bulk correction. However, 1 year later, Engelhardt and Wall have made the generalization of this proposal basically for all orders in H bar, where they have looked at the generalized entropy of a quantum extremal surface and then took the smallest one, the extremal surface that has the smallest minimum generalized entropy. So this is the relevant formula. Now we see that the entropy of the density matrix at the boundary is given by extremizing this whole sum. So it's not just that we're extremizing over the area and then adding subsequently the bulk contribution. We're extremizing the sum and then finding the smallest such contribution. The sum is called the generalized entropy, and it's an important object in quantum gravity, we can say, or ADS-CFT. So in color coding, you can see that all the red lines now here are also encapsulated by this region bounded by X and R. So we're extremizing over both things. Good, so that's the quantum extremal surface. Now one related tool to the quantum extremal surface is something called the entanglement wedge. And the entanglement wedge is basically just the domain of dependence in the bulk, bounded by this quantum extremal surface X and the boundary region R. Here I have presented just one example how this might look like. There's some boundary region R here. This is our quantum extremal surface. This is the region encapsulated by the X and R. And the bulk domain of dependence is everything here drawn very nicely in blue. So all of this region is called the entanglement wedge. And there is a very important statement to be made with respect to this entanglement wedge, which is the entanglement wedge reconstruction. It's a statement about bulk reconstruction, and well, I can just read it. The bulk operator can be reconstructed using some boundary region R if and only if it is contained within this entanglement wedge region. So that's going to be important for these recent developments. So here I have given one example of how this might look like. Another example of how this might look like is when we take, instead of just some region at the boundary, we basically take the whole boundary as our region of interest. In that case, the relevant quantum extremal surface is going to be given by the empty set. It's also called a trivial surface. And it's trivial because its area is equal to 0. So empty set means it's just one point, and so we cannot deform any points. And so it satisfies the homology condition. And since we want to have boundary unitarity, this is just one part of the sum. We also want to add the bulk entanglement entropy, and then both of these. But the bulk entanglement entropy is also going to be equal to 0, since everything inside is going to be given by some pure states. I hope this is clear. And so in this case, when we have the whole bulk to be given in the entanglement wedge, that means the entanglement wedge is the whole space time given the whole boundary, which is just ADS-CFT. Okay, I hope you can hear me still, because it says my internet is unstable, but okay.
We lost a couple seconds there, but I think it's okay now. If it does drop out for someone, please speak up and let us know so we can pause and repeat and stuff.
Okay. Yeah, usually internet here is good, but yeah, okay. Good. So now that I have introduced these tools, I'm going to review some relevant papers from May. Relevant papers were by these authors, Pennington and Mary, Engelhard, Merolf, and Maxfield. And both of these papers are looking at black holes. However, Pennington was looking at black holes made from collapse. And these authors here were looking at eternal black holes. But they exhibit the same behavior in the sense of the information paradox and the firewall paradox. And so we're not going to make any distinction here with respect to that. So what they did in their paper is basically, well, they wanted to see if the system that they're looking at follow the page curve. And now, in order to follow the page curve, you have to have division of the system into two parts. So you have two quantum systems, and you start extracting information from one system to the other. And you want to see how the entropy of these two systems is evolving. If the evolution of these systems is going to be unitary, then they're going to follow something called the page curve.
Sorry, Maria, it's a little bit hard to hear you. Can you, maybe if you have a microphone, can you move it closer or something?
Okay, I can hold it like this. Is this better?
Oh, that's much better. Thank you.
Okay, sorry. Yeah.
Yeah, go ahead.
Okay, so as I was saying, we just divide the system into two parts, and we want to see how their entropy evolves with time. So that's exactly what they did. They divided the system into two, the black hole and the radiation. And what they did was just follow the evolution of the quantum extremal surface, QES, because they want to see how the entropy evolves. And as we have just seen, the entropy is given by the quantum extremal surface. So here is one picture. here we see the division of the two systems into a black hole given here. And this is going to be an auxiliary system that is going to absorb the radiation, Hawking radiation coming from this black hole. So these little arrows here, they're representing Hawking partners. And let's first focus on the black hole. We're going to find the quantum extremal surface, and you can do that before the page time. You can find that it's going to be given by the empty set, like in the example that I was giving before. So it's given by the empty set, so the area of that surface is going to be equal to 0, and the entropy contribution is going to be given by the inside partners of the Hawking radiation. Why only inside? Well, the outside partners, these little arrows here, are going to be transferred to the auxiliary system, and they're going to be separated from these inside partners, and therefore these inside partners are going to have some entropic contribution. And so will the outside partners, but only for the auxiliary system here. So these systems are exactly purifying each other, so the whole system is evolving unitarily. And since these are just the partners of these guys, the entropy is going to be equal for both sides, at least the bulk entropy. So this is S bulk, and this is S rad as in the radiation. And so before the page time, we see that since as the black hole is going to just start evaporating, it's going to evaporate more and more. It's going to be creating these Hawking pairs constantly. The entropy is going to be increasing monotonically on both sides. Now, we can look at this picture, which is after the page time, and we see that it's quite a different picture. For example, now the relevant quantum extremal surface is no longer given by the empty set. It's going to be the surface gamma here that has non-zero area. So why did this happen? We have to remember that the proposal for the quantum extremal surface involves us having the smallest such surface, the surface that has the smallest generalized entropy. And so if we have stayed with the empty surface as the actual quantum extremal surface, we can say just this whole slice here, then we would be collecting all of these inside Hawking partners that are creating more and more entropy as the black hole is evaporating. However, we know that after the page time, or at the page time, so as the black hole is evaporating more and more, and it's creating more and more entropy, the area of the black hole, however, is shrinking. And at the page time, you can say that the area of the black hole has become smaller than the entropy created by these Hawking partners outside. And so because the area has become smaller than the entropy of these guys, it becomes beneficial for the quantum extremal surface to make a jump and to gain some area in order to lose all of this entropic contribution, because we want the smallest generalized entropy. So here is it, like very important orange box. The surface, even though it has non-zero area, it has less entropy than the empty set would. And again, that's because of the inside Hawking partners, entropy is greater than the area of the gamma surface. So this is for the black hole case. And now we might wonder what's going on with the auxiliary system that's absorbing the radiation. Well, if the auxiliary...
Wait, can I ask a question before you...
Yeah.
So I thought when you introduced this quantum extremal surface before, it was basically, you know, like generalizations of Ryu-Takayanagi surfaces where you have some bounded region, you know, on the boundary, and you look at the bounded region in the bulk and you count all of the, you know, matter fields and everything towards the contribution. What is, but here you still have the entire boundary, or...
Yeah, so you still have the entire boundary, and so you're looking at the quantum extremal surface with respect to this boundary. However, you have another system, and so these two systems will evolve globally unitarily. But since you're looking
at that again, it was glitchy.
Oh, sorry. So you are taking the whole boundary for the black hole, but since you have two systems, the quantum extremal surface of interest here is only with respect to the boundary of the black hole. And you're basically neglecting all of this when you're looking at the entanglement wedge of the black hole.
Sorry, so the entanglement wedge is the subregion. Like, do I just count the entire boundary of the ADS and I compute all the matter fields outside this point gamma?
Yeah.
And count those towards my contribution to determine where that surface is. So that'll include all of the exterior radiation.
And the exterior radiation is no longer here. So this is a little bit of a misleading picture, I guess, because all of the Hawking partners outside are actually being extracted elsewhere. So you have two systems. One of the systems is just a black hole with only the inside Hawking partners. And the other system is going to be some auxiliary, completely different space-time. It can be another ADS box. It can be, many ADS boxes. Each of them are going to have one of these outside Hawking partners. So the reason why this jump happens is because you're actually extracting this information outside of your system. In the quantum extremal surface is only with respect to this first system, not the whole thing.
So the matter fields that I would sum over to compute this surface are basically the ones you've got in green here, the interior and the auxiliary.
Right, so these are the outside Hawking partners. I don't know if you can see my arrow.
Right.
Yeah, so those are the outside Hawking partners. See, they're kind of same here, which means like, oh, I'm translating these here. They're not getting detected on my orange slice.
And can you say again why you count those as, I mean, basically you took the exterior modes and you moved them to an auxiliary system, and now you're saying they count as interior.
Sorry, no.
You took the exterior modes, or what I would have thought as the exterior, and you extracted them to an auxiliary system. And your color coding here suggests that you're actually counting that as, along with the interior modes, as things that are still inside.
So right, so this is where I'm going right now. If I can say that this auxiliary system is some ADS space-time that has its own dual CFT, which is the most natural thing to do, then all of this thing is going to be evolving unitarily, right? It's just like with usual two quantum systems. I'm just choosing to look at one of them, but in total, they are evolving unitarily. So if I have this auxiliary system as an ADS bulk to some CFT, then I can assume something called the entanglement wedge complementarity, which is just basically putting in unitarity by hand. Which means that, well, if my entanglement wedge for the black hole is just covering this part here, this orange slice, and my auxiliary system was just this green side in the beginning, then what is covering this part here? Well, it has to belong somewhere, and that somewhere is going to be to the auxiliary system. And so when you connect these slices, everything is still unitary, and the entropy is equal to 0. But now you manage to see how the system evolves and how the entropy evolves for this first system and then for the second system. Because what happens now when I include these inside modes into my auxiliary system entanglement wedge is going to, there are some inside partners here that are completely going to purify these outside partners here. And as the black hole is evaporating, the inside partners are going to be captured more and more, and hence purifying more and more of these outside partners. And so as the black hole is evaporating, the entropy of both systems is going to go down. The surface is getting smaller, it's going to end up here. And eventually it's not going to have any contribution. And complementarily, this region here is going to be bigger, including more and more Hawking partners inside that are purifying these outside Hawking partners. Was that clear? And so we get a page curve.
Thank you.
Okay, cool. Good. So what just happened? We were using semiclassical Hawking's approach to the evaporating black hole, so the calculation that he's done, and put in a new ingredient of how do we actually compute the entropy, which is this quantum extremal surface proposal. And we have obtained the page curve. The unitary is redundant, but I wanted to emphasize it's a unitary page curve, so it's that little triangle. So that inside green region that was in the previous picture, let me show it again.
It's getting really quiet again.
Oh, do you hear me?
That's better, thanks.
Okay. So this inside green region that we had to include by assuming this entanglement wedge complementarity is something that was called the island by these authors here in August. And we see that it needs to be included in the computation of the entropy. Now, that entanglement wedge complementarity, I forgot to say, but it has a little asterisk here. It's an assumption. So it's not something that we can say that this is something that we've proved. It's an assumption coming from very reasonable thinking, which is just, well, the global system has to evolve unitarily. And so it seems like maybe we were putting in the answer by hand. It seems a little bit artificial. However, this islands and this formulation of the quantum extremal surface proposal has been derived from the gravitational path integral, just like the RT proposal was derived from it by Lukowitz and Maldacena a couple of years ago. So that derivation was done by these authors here in, I think, November. And basically, it comes from the replica trick computation that you do in order to evaluate, evaluate the entropy. And these new islands come as new saddles, basically, in terms of Euclidean wormholes in this replicated geometry. So we would have some different replicas. Eventually, we have to take n equals to 1, but it seems that there are some replica wormholes connecting these replicated manifolds. And those replica wormholes will present additional saddles for the gravitational path integral, additional to the original Hawking saddle. And in these papers, it was shown that after some time, after you've included enough quantum effects into your system, or in other words, after page time, these additional saddles start to dominate the path integral. And hence we have a jump of the extremal surface. We have a change. Like in the beginning, the minimal one was the empty one, and then we had to change into the gamma quantum extremal surface. Good. So I believe that by now, there are gonna be some questions, and let me just do that part for you. So we have done, as I said, the Hawking's calculation. We've done Hawking's semi-classical approach to this and used it to get the result. So how come we got a different answer, basically, than Hawking? How come this quantum gives us a unitary evolution? Another question that you might ask is if there is any need for additional new physics, because usually in many of these possible resolutions of the black hole information paradox, we see that there is a need for departure from the physics that we know. So either you have to modify a bit quantum mechanics or effective field theory, something needs to give. And it's not so clear yet if there is any physics necessary here, or we're just using some entropy calculation and the usual Hawking's computation to get the result. Another question that's very important is, okay, this is all an entropic calculation. We have used the boundary, but can we ask a question about the bulk observer? If we put a bulk observer, aka us, into the system, what will we see? What would be the state of the radiation that we see? Similar, very important question is, what would an infalling observer see? So an infalling observer across the horizon, would he experience a firewall or nothing? Those are important questions to ask. Okay. So in order to shed some light on some of these questions, we are going to try to put ourselves into a very, very familiar setting right now, which is a single bulk, single boundary setting. And this is exactly what Raphael and I have done. So instead of putting this path or this auxiliary system outside of the space-time, we're just going to put it in the same bulk that we're working with. And it's going to just be some sphere around the black hole that's going to absorb the radiation. Of course, it's not going to be next to the black hole. It's going to be very far away next to the boundary so that it doesn't get any gravitational back reaction or anything that we cannot control. Now, with this setup in mind, would we get the same behavior as these authors? So let's see. Here's a slightly more complicated picture. So this orange line here is what represents the sphere, usually called the Dyson sphere. So it's very near the boundary. It doesn't get any back reaction. Since this is a thought experiment, I can do it fairly well. Here, this orange line here is representing a star, well, a null shell that's collapsing and making a black hole. These guys here at the horizon are making the horizon manifestly smooth. This is the Hawking picture. The inside Hawking partners and the outside Hawking partners that get detected as thermal radiation. And we see that on the CFD, we have things evolving unitarily. This psi state is just a unitary time psi at some later time. So let's look at these time slices. At time slice 0, so t equals 0, we only see the star and the Dyson sphere. If we move upwards, we can get to a before page time. See, before page time means that the black hole hasn't evaporated that much, and hence it just sees one of these Hawking partners. Of course, that means that after page time, it has seen much more, aka 2 Hawking partners. And eventually, the black hole will evaporate completely, and so this is depicted by this slice T3 here. Of course, we want to draw a global slice in a sense, so we have to include this disconnected piece here. So this is all T3. So Hawking radiation is absorbed into this path, into this Dyson sphere, and by definition, the global bulk state is always pure. So this slice here sees everything happening on it, and so do these two. And so does this third slice if we include this inside of a black hole. This is just slicing. It doesn't say anything about the bulk observer yet.
Sorry, but the T3 slice is no longer a Cauchy slice, or is that not required by your?
No, it's not it's a disconnected slice, basically. You can consider this a disconnected pinched off black hole, and this to be just a full slice. And I agree it's not a Cauchy slice because you have to go very time-like in order to get there. But we still have to include it for the purposes of boundary unitarity. And it's okay in that case to have disconnected slices. But I will come back to this exact point. This will be important.
Okay.
So, can you also elaborate on the point Hawking radiation is absorbed into the bath? Like how do you represent it?
How would I? Sorry, what?
The microphone.
Sorry, the microphone was far away. I was just inquiring. Can you expand, please, on Hawking radiation is absorbed into the bath? Like, what exactly you want to do?
Okay, so we can basically consider this Dyson sphere. You can imagine, like, I have a black hole, and then I have a huge sphere around this black hole. And as the black hole is evaporating, all of the Hawking radiation is getting just detected on the Dyson sphere and just being absorbed there. It's just like in this case of with the auxiliary system, where we were just putting it in some auxiliary spacetime. Here, instead of introducing some auxiliary spacetime, we're putting everything within one bulk. So absorbing the Hawking radiation inside that one bulk.
But
it's like saying.
When you say absorbing, you mean you mean a projective measurement, or what exactly do you mean?
Basically, just collecting all the Hawking radiation, if you will, so that I can do some measurements with it later and analyze it.
So basically, what you mean is basically decoupling, in the sense that, like, you just do not allow it to interact with the rest, and it does what it wants to do. This is what you mean.
Right. So it's like in the previous setting. I just want to extract it from the black hole and collect it in one place, and then in that one place I can analyze what's going on.
Okay. And
Okay.
the Dyson sphere is it gonna have some dynamics on its own, or?
No, the Dyson sphere can be some just very large sphere. Since it's a thought experiment kind of a sphere, we can make it very large without back reaction. It's in asymptotically far away region, and its only purpose is actually just to get these Hawking modes
Okay.
detected. Yeah. Okay. Thank you. Okay. So, right. So we have seen that when we put stuff into one bulk, the relevant quantum extremal surface, since the bulk state is always pure, is going to be given by the empty set again. And all the modes detected on all of these slices are going to be entangled, but they're going to purify each other. And so the whole bulk state is going to be pure. So it doesn't seem like we can get an island, for example, inside the black hole, or a jump of the quantum extremal surface. And we would like to see that happening as well. So in order to get these islands or the jump of the quantum extremal surface, we're going to absorb this Hawking radiation into the Dyson sphere, but then we're going to transfer it along it into a near boundary reservoir that's very much localized. So the picture would look something like this. This is just a slice of the ADS now to nicely depict what's going on. This green circle here represents the black hole. This orange circle is the Dyson sphere. And this is the reservoir in which we're going to just collect all of our Hawking radiation. So the black hole evaporates, it's spewing out some Hawking modes, they get detected here, and then they get sent to this reservoir here. So this is the main mechanism. And now you can see that there's a difference with respect to the previous settings, because now we're choosing a specific region at the boundary. We're not looking at the whole boundary. We're choosing a specific region at the boundary that's going to have some entanglement with the rest of it, but that's going to be just constant. And then we're just going to look at the RT surface of that boundary itself. And we want the reservoir to be inside this out region, as I called it before.
Wait, so all the radiation you collect on the Dyson sphere gets piped into this region R?
Right.
And then what's
into this region, into this little blue box. The region R is on the boundary.
So the only entanglement is between the blue box and the black hole now.
Right. Yeah, that's the thing that I wanna consider here. Of course, you're gonna have some entanglement here, but that's just gonna give you some constant contribution.
And so you can that it takes some time, pi and ADS units, to get the like radiation on the far side. It takes some time to propagate over there, which by that point the black hole has evaporated.
I'm guessing, since I can guess that I can always direct this Hawking radiation to come in such a way that it's going to be all in good times.
You sort of like bend it around as it comes out the far side, so it gets there rather than having to go to the far boundary first.
Right, and plus the black hole is evaporating quite slowly. So since it's it's a very slow effect, and these Hawking modes are traveling quite fast.
No, but I mean, the time scale it takes for radiation to cross through the bulk is from one side to the other is also the same as it takes for a mode to go from one side of the boundary to the other, right? So if you have modes from the far side of the boundary, yes, I'm not sure it works for like this.
I did not get any of that.
Okay, it's probably not important for your analysis then. Go on.
Yeah, we can just assume that these things get there in time. Also, this picture is a pre-page time picture. So I'm assuming that I started with large enough black hole.
Right, I was just concerned about the fact that the radiation that ends up on the far side from the blue
like
box.
Here.
Yeah, the amount of time it takes to send that around the boundary to the blue box is basically the same time scale it takes for radiation to get from the bulk to the boundary in the first place. So I was just worried about the order of events there. But it might not be important, so why don't you just go on and I'll see.
Right.
I won't worry about it.
So maybe the curve is going to be a little bit different, but the point is that the shape of the curve is still going to be the same. We want the curve to go up and then down at some point, right?
Okay.
Right. So as I said, this is before the page time. So before the black hole has evaporated half of its size, After the page time, however, this region here has to include the region inside the black hole. Remember, this is a region that we're looking for the radiation, so for the outside Hawking partners. And just as in the case for the auxiliary system coupled to the black hole, this quantum extremal surface has to develop some disconnected component, which is going to be the interior, for the exact same reason that it happened with the auxiliary system. So after the page time, the area of the black hole shrinks, and so it becomes more beneficial for the surface to actually jump and to include some area in order to exclude all of the inside entropic partners. So it's the exact same story as before, just with a slight modification. So here we get a page curve as well. Okay.
Also, it looks
yeah.
a bit like so it looks a bit like regular Ryu-Takayanagi, but for large enough subregions, right?
Right, exactly. Yeah, it's exactly the same system. Sorry, the same effect that happens, for example, for entanglement plateau.
Yeah.
In that case, you would just, instead of fixing this region R in size, in that case, you would just be expanding the region R, including more and more stuff in it, basically. And so at some point, it just becomes beneficial for it to include just the entropy of the black hole, so, which is just given by Eteria, than to keep growing as it was. So this is the same effect. We're just moving stuff around now, putting it inside. So it's not like this, the boundary region is getting bigger. We're just putting in more and more entropy, and so the same effect happens. So yes,
but this is just a thought experiment, right? Like it's hard to quantify the calculation.
Yeah, it's a thought experiment. It's a qualitative description of what would happen. So we didn't compute any of these things, but just going through the logic of the process, it's very reasonable to expect that the system is going to evolve in the same way as before. It was just easier for authors before to have an auxiliary system or to couple the black hole to some flat regions in order to have computations more readable. But that's also an approximation that you can do. It's also not something that you would expect. I mean, it's just an approximation that you're gluing flat regions to your ADS spacetime, although a very good one. But yeah, I agree. It's a thought experiment.
But can you do something similar without invoking the Dyson sphere and localizing all the quanta in some region in the bulk? This is, like just let the black hole in ADS evaporate and like the thermodynamically unstable one, like let it do its thing, and try to conclude something similar, or like that.
I mean, that's what we're doing here, right? So we took the large ADS black hole, which would be, yeah, so we're, I don't know if I mentioned this. This is a pretty big thing. So the reason why we're doing this coupling to the bath in the auxiliary system or putting this Dyson sphere around in this ADS spacetime is because we're dealing with large ADS black holes. And so large ADS black holes are known to be so large that the Hawking they put out actually comes back in before they can evaporate completely. So they're in thermal equilibrium. But they are the ones that we know how to work with and we know how to calculate using the ADS CFT, of course. For the small ADS black holes, they behave just like in Minkowski, and of course we expect the same behavior, but we don't know how to characterize them using ADS CFT. And that's why it was important for us to put either some absorbing boundary conditions at the ADS boundary or to put in some additional sphere which would collect all of these modes in order to study this behavior here.
Also, so basically you want to make the black hole evaporate by collecting the Hawking quanta.
Well, the black hole is going to evaporate no matter what I do, because if it's immersed in quantum fields, if I just include quantum effects, it's going to evaporate. The point with the large black hole is just it doesn't manage to evaporate because it gets refilled with Hawking quanta all the time because it's too big. It's a ball in a box and the ball is too big. So it doesn't have time to get shrunk down. I don't, yeah. Was there a question?
No, that was good. Yeah, it was good.
Okay. Okay, good. So now that we have this familiar setting here ready, one thing that I should mention though, this existence of the quantum extremal surface inside, we see, as somebody has pointed out, it's a very natural phenomenon that happens also for the entanglement plateau, and it happens only because of the homology condition. I didn't have to assume anything artificial or assume something that I don't know if it's true, like entanglement to wedge complementarity. It just comes out naturally from the homology condition. So that's one advantage of this system. So now that we have the system, we can ask a question. For example, what does the bulk observer detect? In the previous settings, it wasn't that clear how my bulk observer is going to actually interact because I have all of these additional auxiliary systems. But now I have just a single bulk and a single boundary, so I know exactly how to work with my observers. And so basically asking the question of what does the observer detect is the question of what is the state of the outside radiation. So going with the most naive face-on interpretation of these results is that because we use the Hawking's computation, we ought to get the mixed radiation. In other words, we would be getting information loss in the bulk, and subsequently, because we consider ourselves to be bulk observers, we would be getting information loss. However, we've seen that the RT prescription, the quantum extremal surface prescription, gives us boundary unitarity. So these two things seem to be okay with each other. The bulk observer can experience information loss while the Ryu-Takayanagi prescription gives us boundary unitarity. But it still looks like something is wrong, and we can ask a question, is this actually compatible with ADS-CFT, even though it's compatible with RT? And it turns out that it's not. And it's not compatible with one very important ingredient of it, which is the ADS-CFT dictionary. So let's go back to our more complicated setting, because it's easier to analyze, where we have the Dyson sphere just collecting. It's the Dyson sphere not localized anywhere, it's just collecting all the radiation here. And so after the black hole has evaporated, it has collected all of the outside Hawking partners into this Dyson sphere. And so at this T3 slice, I have all of the Hawking outside partners in here. Those outside Hawking partners are by definition mixed. And since this Dyson sphere is going to be near the boundary, I can just use my boundary dictionary, bulk boundary dictionary unit to deduce that my boundary states should also be mixed, right? Since the states, we know how to use the dictionary near the boundary. And so this already seems like it's contradicting the basic, well, I started with the pure state and now all of a sudden I have a mixed state. So you might just say that there's a contradiction right there, but you might also think that there are some other degrees of freedom that can purify this state. Because there were examples in the past where we would have, in the near boundary region, you would have a mixed state, but that wouldn't mean that the boundary itself is in a mixed state, because there would be some dilute degrees of freedom that would purify this state. I do mean dilute, because dilute in the sense of low energy degrees of freedom, which respectfully in the bulk means just that it's deep in the bulk. So stuff deep in the bulk, it manifests itself energetically on the boundary as very small energy. Stuff near the boundary is higher energy. It's just the usual ADS-CFT. So we could think that maybe in this case, there will be also some purifying degrees of freedom. However, that would require some energy. Why? Well, my CFT lives in a sphere, and so it's a compact manifold, and so any excitation would induce some additional energy, and any purification that I would want to use for this mixed state would also require some additional energy. But I have already accounted for all the energy of the CFT. Remember, the energy of the bulk and the energy of the CFT have to agree, and as we see in the beginning, we had some zero slice that was just connecting this. It just had in the energy just the star and the Dyson sphere that was empty. By the end of the evaporation, it just has a Dyson sphere that collected all of the Hawking information. The outside Hawking radiation. And so the energy has been conserved all the way. And so the energy should be the same on the CFT. So it seems like I don't have any room in the CFT for this purification. And hence, since I have no room for the purification, that means that I'm left with a mixed state at the boundary. And so I get a direct contradiction. And this black hole here that actually carries the actual purification of these modes here, it's a disconnected manifold and it cannot contribute any energy to the CFT. And so I cannot use it in order to purify this state. So we could have made this picture. This is just a picture of basically a more detailed analysis of the problem that we could have done in 97.
Can I ask about that? Why? I mean, the black hole should be living in the CFT somewhere, right? Like, I mean, the CFT should have a complete
Well,
of the bulk.
right.
Why do you say it doesn't contribute to the energy of the CFT? The black hole?
This, as you noted before, so this is a disconnected Cauchy slice. So it's just a disconnected manifold, basically, that doesn't contribute the ADM energy. The ADM energy you have to always detect it in the near boundary region. It's just how the definition
in
of
the bulk,
energy is.
yes.
Yeah, but then we're using that energy in the bulk in order to see it in the CFT.
So you mean there's a mismatch between the energy in the bulk and the energy I would expect in the CFT?
The energy is conserved in the bulk. So in the bulk, I started with some empty Dyson sphere, started with some star that made the black hole. And I took away all the thermal radiation. So the black hole has completely evaporated. It's no longer in your space-time. And all that you're left with is the Hawking radiation. And the energy is conserved in that case. So there's nothing in your CFT that you can use to induce more energy.
Can you repeat that? That was a weird glitch there thing. Are you saying all the energy, because the black hole is gone, is in your Dyson?
Yeah.
So there is no black hole anymore.
It's somewhere disconnected. It's a pinched off black hole if you want. And it's no longer a part of my CFT.
Okay, thanks.
Good. So we see that we have a problem with the dictionary if you just assume that the state is going to be mixed in the bulk. However, that is what Hawking told us. But interestingly, though, there is another interpretation to these results, even though we use the Hawking's calculation. And if you've seen Douglas Stanford's talk last week, you might know what I'm talking about. Otherwise, I might sound crazy. But let's say, for example, that if the bulk is dual to some ensemble of theories and not just one theory, we can ask a question if we still get a problem with the ADS-CFT. So this ensemble of theories is something that has been explored in the papers from the Stanford group before and subsequently in these replica wormholes papers as well. And the statement is that there exist such bulks that are dual to ensembles of boundary theories, so not just one unitary theory. And so these papers have, of course, analyzed these properties in much greater detail. I just want to put out a simple analysis here that would help us understand what's going on with the state. So we would have several members of an ensemble, and each member will be a theory, a CFT theory. And so within each member of the ensemble, we have unitary processes. So we would have in states that are pure evolving into pure out states. And so, and for all theories, these processes would happen. And so within each theory, the entropy for these processes would always be 0 because we are evolving pure to pure. And we can take an average of this entropy, and the average of the entropy would still be equal to 0 because the average of 0 is 0. However, if we take an average of the pure out states, we would not get a pure state. We would get a mixed state by definition, basically. And so that would be actually consistent with the bulk evolution, which would give a mixed state as well. So we would have mix to mix state. And that would be okay. There would be no loss of unitarity within each of these CFTs, because we're just taking their average and then evolving that average. And the average, of course, is not going to evolve unitarily. So this would be consistent with the bulk evolution. Of course, this interpretation and everything that I've said has some caveats. In the end, at the end of the day, unitarity demands that the outstate should be pure. And so we are getting a mixed state out of these calculations. So what is going on? Well, one thing that we can say is that the semi-classical approximation can only give us so much. And that the Euclidean path integral, even though it's giving us correct result for some things, it doesn't seem to know about everything. And a more technical way of putting that is that the Euclidean path integral might know only about so-called self-averaging quantities. Those are the quantities whose variance is very small, or the ones which are well described by the averaged value of the quantity you're looking at. So for example, entropy would be one such quantity, since we've seen that the path integral is giving us a result that we would expect from a unitary theory. However, the state is definitely not such a quantity. It's giving us a mixed state, and we expect to get a pure state out. So maybe with this, I can ask another question. What about firewalls? We have put that in our list of questions. Well, as I have said, we have gained a mixed state, but we expect a pure state, and it came out of a path integral. So we cannot really trust the path integral with respect to the state. And if I don't know what my state is, well, then I cannot say very much about firewalls. They require us to have pure radiation out. Even though in this picture, naively, it looks like the horizon would be smooth because of the Hawking picture, we are not going to trust the path integral on that one yet. Good. And so with this, I can maybe conclude. We are definitely learning a lot of new things, and we now know a lot of new things. And for example, one important development that we have seen is that the quantum extremal surface proposal is a conjecture, and the entanglement wedge reconstructor as well. But we have seen that they have very compelling evidence for coming from these developments. That the compelling evidence is that we're seeing the unitary evolution of these systems thanks to these proposals here. Another thing that we are learning about is the importance of islands, or in other words, other saddles in the path integral. We have always known that there are going to be other saddles and such so forth, but the importance comes into play when there is an exchange of dominance of these other saddles. So like when I was explaining for the replica computation, we had the original Hawking saddle, and then we had the additional saddle of wormholes, which was suppressed in the beginning, but then started to dominate after some time. And that was not an effect that we have seen before. And so maybe in the end, also one thing that we're learning about is that they might be a new formulation of the black hole information paradox. It's kind of a puzzle that we're getting the right answer for the entropy and not for the state. So you might call it also state entropy formula. But I would like to say that my words would be just that the path integral is very clever, but also very cheeky for not giving us, the final resolution, the entropy 0, but not giving us the state from which we get that entropy. And so thank you for listening.
Thank you. Any questions? I have one if nobody wants to.
Okay.
So, so if I understood you correctly, your system with the Dyson sphere, when you moved the entropy to one point, this basically enables you to run this story with the islands without having to invoke some auxiliary.
Exactly.
Okay, cool. So that's kind of neat.
Yeah.
But then in that auxiliary story, if I wanted to talk about unitarity and such, like you did at the end, what happens with the auxiliary system? It just hangs around, and if I want to speak about whether the final state is pure, I need to always talk about my original bulk plus this auxiliary system, or
Right.
you know how
Yeah.
that's treated? So I
Right.
never basically get back. I just have to hang around with the auxiliary system the whole time.
Right. So one nice way, so the auxiliary system that I was presenting it was basically the version that Pennington did at his paper. He just took an ADS spacetime and then connected it to various ADS spacetimes, each of which would have one Hawking quanta, so it's not to back react or something like that. And each of those additional ADS spacetimes would be auxiliary systems. Of course, you can lump them all into one auxiliary system. It doesn't make any difference for the principle of the discussion. However, in the paper by Almeri et al., they took an ADS to black hole and then coupled it to 2 halves of the Minkowski spacetime. So it kind of looks like a Schwarzschild black hole in flat spacetime. So it looks kind of more natural, but it's still coupling of 2 flat regions to the black hole. And there you can do very explicit calculations. And, well,
this always seemed odd to me because of the time-like stitching conditions along the boundary. But your construction, so the thing you did in the paper with Rousseau was basically have this Dyson sphere that avoids all that.
Right.
Okay.
Yes.
Okay. Cool. Thank you.
And it also allows you to ask questions like what happens to these observers and stuff and such without going to the boundary.
I have one more question. Thanks. Thanks also for this very nice talk. I really enjoyed it.
Thank you.
And do you know other examples of possible traces of ensemble averages in holography? Like for example, like in the like in the standard ADS-50, like dating back to I don't know, late 90s, like early 2000s, right? And like this would not be something that you would basically came up with, right? Like you would think, oh, like there's something unique, like the thing that the gravity does is unitary, the thing that cyclically unitary, the thing that you get on the boundary is unitary by definition. You compare and like manipulate.
Okay, I missed the last 15 seconds.
Oh, sorry. No, very good. So my question was about other examples of evidences for self-averaging in holography, in particular in higher number of dimensions.
Mm-hmm.
Like
right. So I have no idea actually. That's a very interesting question because so far I think that the only known ensemble dual is the one with the JT and SYK. But I'm really not sure about this. There is a really nice paper by this group from Stanford that deals with this in detail, and also their papers from before. I'm guessing that they would have some references to other examples like that.
Yeah,
but
thanks.
I agree.
My impression was that this thing arose in SYK because SYK was defined with respect to some ensemble average, and then well, I mean, like then you can start wondering like maybe it's more generic, but okay. I'm glad to hear that actually this is a bit unsettled.
Yeah, it's very settled actually. Also, there's a question: what happens for the non-average theories that we know that are not part of the ensemble? For example, n equals 4 SYM. Like it would be very weird to assume that it's a part of the ensemble. We have such an exact dictionary between these things, and it's a
that was the origin of my question actually. Yeah.
Right. Yeah. So there is a discussion about these non-average systems, but as far as I can tell, there hasn't been anything conclusive yet. The one thing that you might imagine doing is that you imagine it was a part of an ensemble, compute some quantities and see if they would be acting as self-averaging. And if they do act as self-averaging quantities, then you can trust the result that the path integral would give you. Otherwise, you shouldn't trust the result. So for example, if you wanted to check, I don't know, maybe like if there are firewalls or something, you wanted to check the relevant quantity for that, that will be the stress tensor across the horizon. And so if you see that the stress tensor is actually self-averaging, then you might go ahead and try to use the path integral in order to get some result for it. But this is all very early and very developmental, and I highly encourage you to read these new papers.
Thanks.
Any other questions?
So can you ask what happens with the singularity at the end of the evaporation process?
What about the singularity?
You have to come here. Sorry.
So I wonder, in this picture, what happens with the black hole singularity at the end of the evaporation process?
So we can completely basically ignore the issue of the singularity when it comes to this analysis of the entropy. We can draw these nice slices, and they don't ever come across the singularity. And eventually we do expect for the singularity to just, when the black hole evaporates, and so small, carry in information, and so we don't expect it to change qualitatively the picture that we have for the entropy.
So, but like your final bulk space-time has two boundaries or one boundary?
So in my Dyson sphere example, it's like one boundary.
Okay.
It's one bulk, one boundary, yeah.
So your final space-time is just ADS?
So I started with black hole, that's an ADS, the large ADS black hole, and I let it evaporate, and after if it evaporates, with respect to my CFD, I'm just left with empty ADS with some Hawking radiation inside, aka this Dyson sphere.
Okay, thank you.
Maybe anybody else online have a question? Okay. If not, then let's thank Marija again for this really nice talk. Thank you.
Thanks.